So, welcome back to lectures on engineering mathematics 2, and this is lecture number 42 on Fourier sine and cosine integrals. So, today we will discuss what are the Fourier cosine integrals and Fourier sine integrals, and then some worked problems based on these concepts. So, coming to the Fourier sine and cosine integrals. So, in the last lecture we have seen that the Fourier integral representation of a function f is given as this a alpha cos alpha x, b alpha sin alpha x and d alpha, this integral, where these Fourier integral coefficients a alpha and b alpha were given by these infinite integrals minus infinity to plus infinity, and b alpha was given again with this improper integral minus infinity to plus infinity f u and sin alpha u d u. Well, now the point is, if we consider that this function f is an even function, or suppose the function f is an even function, then what will happen, whether there will be some simplification to the representation, to the Fourier integral representation. So, naturally, because if this f is an even function, then what will happen to, for instance, to this a, f is an even, cos is also even. So, here the integrand will be the even function, and in this case, since the sine is sitting there with f u is even, but sine is odd. So, this will be a odd integrand to this function. So, in this case, this b will go to 0 because the integrand is odd, is an odd function, and because this integrand is an even function. So, we can write instead that 2 over pi this integral minus infinity to plus infinity and f u and then cos alpha u and d u. So, these with these simplifications we want to now go. So, if this f is an even function, then we have this a alpha 2 times 2 over pi integral, instead of this minus infinity to plus infinity, this has become 0 to infinity f u cos alpha u, and then b alpha will become 0. So, this Fourier integral representation, this term will vanish, and then we have a rather simple integral representation which is 0 to infinity, and then we have a alpha and cos alpha x d alpha. This is again similar to what we have done in case of the Fourier series as well, and similarly there also the b n's were 0 for the function f, which is an even function, and for the odd function the other way round. So, thus for an even function we have this Fourier integral representation, and now similarly when we have an odd function f, then the a alpha will become 0 and the b alpha will be computed by this 2 over pi 0 to infinity f u and sin alpha u d u, and its Fourier representation will take this simplified form as b alpha and sin alpha x d alpha. Just a remark here, which is very important for the discussion now, similar to the half range Fourier series. So, if you recall the half range Fourier series, the idea was entirely different there, where we were extending the function which is defined in the 0 to L interval, and the way we extend the function in minus L to 0, the corresponding either the sine series or the cosine series will appear, because if we make the entire function defined in minus L to L as an odd function, then we will end up with the sine series, and we extend the function in terms of so that the function became even function, then we will end up with the Fourier cosine series. Though we can have infinitely many extensions of this function, but we have chosen those two extensions to make the overall function minus L to L as an even function or an odd function, so that we get some simple representation either as a sine series or cosine series, and both of them will be valid for the, or will represent the function given in 0 to L. A similar structure we have here as well, that we can represent a function which is defined, for instance, for all real x. So, a function is given which is defined for x positive, and now by defining or by extending that function as an odd function or an even function over the entire real axis. So, for instance, we extend this from minus infinity to 0, so that the function in the whole real axis become an even function. Then we have this, that simplified representation where a and a alpha will survive and b alpha will become 0, and we have the rather simple representation with that a alpha. Or if we extend this function from minus infinity to 0, so that the function defined in the whole range now becomes an even odd function. In that case, this a alpha will be 0 and b alpha can be easily computed with the help of this integral, and the representation will be simpler now in terms of only this b alpha and sin alpha x. So, with this idea now, let us just consider, for instance, a function is defined here in 0 to infinity by this curve. So, we have the possibility of this extending as an odd extension or an even extension. So, if we extend this as to, so that the whole in the whole real axis the function has become now an odd function, then its representation will have only this b alpha terms, and then we have this simple representation. On the other hand, if we extend this in this way, then this will become an even function, and if we write its integral representation, that will have only the cosine term, only the cos term in the coefficient and as well as in the in this integral representation. So, these are the two possibilities where we can make use of the function defined in the interval 0 to infinity. So, only in one half of this axis the function is defined, in the other half we can define according to our wish to have either a Fourier sine integral representation or to have Fourier cosine integral representation. So, when a function is defined in minus infinity to plus infinity, we will have a Fourier integral representation which will have in general both the terms sine and cosine, but when the function is defined in 0 to infinity, we have the possibility to have either only sine functions in the representation or only cosine function in the representation. So, that will be the discussion of this chapter now. So, we have this result we can summarize now. Suppose f is a piecewise smooth function, the conditions are same as discussed earlier on every finite interval on the positive axis, and let f be absolutely integrable. I mean, that is important here for that transition from Fourier series to this Fourier integral representation. We have additional condition on f to be this absolutely integrable. Then f may be represented either by the Fourier cosine integral, that is the first possibility we have discussed, and the Fourier cosine representation is just 0 to infinity a alpha cos alpha x, where a alpha is given by this integral. The second possibility would be that we can have the Fourier sine integral, which can be written here b alpha sin alpha x, and b alpha will be given by this coefficient 2 over pi 0 to infinity f u sin alpha u du. So, without this formally extending the function from minus infinity to infinity, that is the idea behind, but we can directly use these results if we want to have the Fourier integral Fourier cosine integral representation. We will compute a alpha by this formula 0 to infinity, and f u is given in 0 to infinity. So, there is no problem. Similarly, if we want to have, we wish to have the Fourier sine integral representation, we will compute this b alpha, and then we can represent this f using this sine representation. Well, so moreover, the above Fourier cosine or sine integral converges. The convergence is exactly what we have already discussed in previous lecture for the integral representation. So, that these integrals will converge to the average value, and at the point of continuity the convergence will be to the function value itself. Well, so we consider this problem now, that this function which is defined 0 as in the range minus infinity to minus pi, then minus pi to 0 it is minus 1, 0 to pi 1, and then pi to infinity 0. So, we have the function here which is 0 up to this minus pi, and then pi to 0, then pi. So, minus pi to 0 the function value is minus 1, and then we have 1 there in 0 to pi, and then again 0. So, we have this piecewise continuous function, and we want to find the Fourier integral representation of this function. So, what is to be noted in this case, that this function is an odd function. So, here whatever values we have for the positive one, it is just minus of that in this negative range. So, this function is an odd function, and naturally this a alphas will become 0, and we have to only compute this b alpha. But the point is, here the function is defined in minus infinity to plus infinity. So, we are writing its integral representation, which is automatically coming as the sine integral representation. But so, in this case we are not having the possibility of choosing whether sine integral representation or cosine integral representation, because the function is defined from minus infinity to plus infinity. Whereas, in the next examples we will see that when the function is defined in 0 to infinity, then we have both the possibilities, whether we want to have a Fourier cosine representation or Fourier sine representation. So, in this case, since the function was defined from minus infinity to plus infinity, we will simply write its Fourier integral representation, and finally, the question is that to what value does the integral converge at x is equal to minus pi. So, that we will also discuss. The given function is an odd function that we have already noticed, hence the a alpha will be 0. So, that is the automatic calculation here, because of this odd function the a alpha will be 0, and the b alpha we can compute with this help of this integral, which have now 2 there and 0 to infinity. So, instead of minus infinity to plus infinity, since the function is odd, we can just compute in this 0 to infinity f u and sine alpha u. So, this the function is given already, that 0 to pi it is 1. So, 1 into this sine alpha u, and this can be integrated now to have cos alpha u over alpha. So, we have 2 over pi alpha and then cos alpha. So, we can put this with minus sign. So, minus cos alpha will be coming. So, we have the with this pi we have cos alpha pi, and then 0 we have 1. So, the value of this b alpha coefficient is 2 over pi alpha and 1 minus this cos pi alpha. The Fourier integral representation, because a alpha is 0. So, in this case we have a rather simple representation, f x is given by 2 over pi, we have this 1 minus cos alpha pi over sine alpha x dx. And now, the question is that to what value does this integral converge. So, we have the Fourier integral representation of the function. Now, the question is to what value does the integral converge at x is equal to minus pi. We know the convergence theorem already. So, wherever the function is continuous, it will converge to the function value, and if the function is not continuous, it is discontinuous, then we will take the average value of the function at that point. So, for instance, at x is equal to minus pi, indeed this function is not defined at x is equal to minus pi, but does not matter, we can take the value, we can take the average value of the limits at that point. So, about the convergence, at the point where it is continuous, it will directly go to the average value. So, for instance, in the range minus infinity to this minus pi, the integral, the Fourier integral will converge to this 0, and then at pi, when you have x is equal to minus pi, it will converge to the average value 0 minus 1 by 2, and then in the minus pi 2 x into 0, it will converge to minus 1, and at x equal to 0, it will converge to again average value minus 1 plus 1 by 2, which is 0. Here it was minus half, and then when we have 0 to pi, it will converge to 1, and then at pi, x is equal to pi, it will converge to 1 plus 0 by 2. So, the half, here it is 1, here it is 0, minus 1, minus half and 0, and then when x is greater than pi, then it will converge to 0. So, we have convergence at all points here. Wherever the function is continuous, it will converge to the value itself, and wherever it is discontinuous or the function is not defined, at those points we will take just the average value. So, the question was at x is equal to minus pi, we have already discussed. At x is equal to minus pi, it will go with this average value, which is 0 minus 1 by 2, and then we have minus half. Well, so we will move to the next problem, where we have to find Fourier sine and cosine integral representation. So, now in this question, we need to find Fourier sine as well as Fourier cosine integral representation of this function f, which is defined one in this range 0 to pi, and then we have here pi to infinity as 0. So, the given function is in the 0 to pi is given as 1, and then it is 0. So, after that it is 0. So, the function is defined by this curve, and now in this case it is different from the earlier one, where the function was defined in the entire interval minus entire real axis minus infinity to plus infinity, but now the function is defined in 0 to infinity, and now we have the possibility of extending this in this minus infinity to plus infinity. If we extend it as in this way, then this will lead to a Fourier sine representation, or if we extend this in this way, then it will extend to a Fourier the cosine Fourier cosine integral representation. If we extend to have this odd function, then we have the Fourier sine representation of the given function. So, we will see now, and the question further is that evaluate this integral 0 to pi sin pi alpha and this cos pi alpha over alpha, and also this 1 minus cos pi alpha sin pi alpha over alpha d alpha. So, after evaluating this Fourier sine and the cosine representation, we will see that we can easily evaluate these integrals there. So, coming to the Fourier sine representation, where this function is basically extended to have an odd function over the whole real axis minus infinity to plus infinity, we can write down its Fourier sine representation. So, this f x as this b alpha sin alpha x d alpha, where this b alpha is given by 2 over pi f u and sin alpha u du. The f is defined 0 to pi as 1. So, we can compute this 0 to 2 over pi, we have 0 to pi, because it is only defined 0 to pi, rest it is 0, and then we have 1 into this sin alpha u. So, which can be now integrated. So, we have this cos alpha u over this alpha and then 0 to pi with the minus sign because of this integral, and then we have this 2 over pi naturally sitting outside. So, here 2 over pi, since it is a minus. So, first we will put this 0. So, we have 1 over alpha and then minus we have cos pi alpha over this alpha. So, which is written here 2 over pi 1 minus this cos pi alpha divided by this alpha term. So, in this Fourier sine representation, we have computed this b alpha as 2 over pi 1 minus cos pi alpha over alpha. This is the Fourier coefficient, and therefore, we can write down this representation, the Fourier sine representation with this coefficient here 1 minus cos pi alpha over alpha and sin alpha x d alpha. So, this is the Fourier sine integral representation of the given function. Now, if we look at the desired integral, which will be coming from this representation itself. So, this was the question, that what is the value of this integral here. So, if we compare with this Fourier sine integral representation, what we notice that this 1 minus cos pi alpha that is sitting exactly like this. We have sin alpha x, but here we have sin pi alpha and then over alpha d alpha. So, if we take here x is equal to pi, if we take x is equal to pi, then we can get this desired integral which was asked in the question. So, at x is equal to pi, then we have to also look at what is the convergence. So, x is equal to pi, again this function is not defined, and therefore, we have to take the limit. So, f pi plus and then f this pi minus divided by 2, this average value, that Fourier integral at x is equal to pi will converge to. So, here f x pi plus is 0 and then f pi minus is 1. So, divide by 2. So, it is half. So, that Fourier integral at x is equal to pi will converge to this value half. So, if we substitute this x is equal to pi in this above integral, we will get exactly that integral which is the point of question now. So, here we have 2 over pi 1 minus cos pi alpha over alpha, and sin this x is replaced now with this pi. Sorry, so x is replaced by this pi here. So, we have the desired integral coming, and then this value is equal to half, because that is exactly the average value of this function at x is equal to pi. So, the value of this integral is 1 by 2 or this pi by 2. So, this can go to the other side. The value of this integral here is pi by 4. So, as we can notice that this integral, it is not easy, it is not simple to compute directly, but with the help of this convergence theorem and the Fourier integral, we can see that such complicated integrals can be evaluated easily, and that is one of the applications now we do see in the computation of these complicated integrals. So, coming to the Fourier cosine representation, where we have to extend the given function to make it as an even function, and then its Fourier representation will be having a alpha computed using this 2 over pi 0 to alpha f u cos alpha u du, and this we can compute as 2 over pi 0 to pi, and the value is 1 in 0 to pi, otherwise it is 0. Then we have this cos alpha u du. So, this will be the integral will be sin alpha u over alpha, and then we have 0 to pi, and 2 over pi is sitting outside the integral. So, this value will be 2 over pi, and sin when we put there. So, we have sin pi alpha over alpha, and then minus that will be 0. So, this is the value of the integral sin pi alpha over alpha with 2 over pi factor. The Fourier cosine representation now, because we have already a alpha, we can substitute in this representation. So, the f alpha will be represented by this integral here 2 over pi, we have sin pi alpha over alpha, and then this cos alpha x from the Fourier this integral representation. So, this is the Fourier integral representation of the cosine integral representation indeed for the given function. And then the question is that what is the value of this integral, which is sin pi alpha cos pi alpha over alpha d alpha. So, if we compare with this now, we have sin pi alpha, here also we have sin pi alpha, we have cos pi x, we have cos pi alpha. So, again if this x is replaced, if is substituted by pi, then we are getting exactly this integral. So, again to get this desired integral, we have to use x is equal to pi. So, if we substitute this x is equal to pi into the above integral, then we can exactly get the desired value there. Now, the question is again that x is equal to pi, this integral will converge to again to half, because we have this average value f pi plus and f pi minus divided by 2. So, f pi plus we have 0 and then we have 1 divided by 2. So, the value is 1 by 2. So, this value we have 1 by 2 and then this integral is set to be equal to half, and again we have this value pi by 4 for this integral. So, again such complicated integrals can easily be computed with the help of this convergence theorem and this Fourier integral representation. Well, so here we have these references which are used for preparing this lecture, and now just to conclude that this Fourier integral representation, which was given as a alpha and this b alpha term with cos alpha x and sin alpha, which usually or in general it has the cos terms as well as the sin terms. But what we have seen in this lecture, that for even functions, so this if f is an even function, then the b alpha will be simply 0, and for the odd function the a alpha will become 0, and we can just compute b alpha there, and in this case we need to just compute a alpha, that to a much more simplified integral. What was the interesting here, we have seen that if f is defined only in 0 to infinity. So, earlier case this was when the function is defined in minus infinity to plus infinity, and it is given that it is an odd function, or we notice that it is an even function, then the calculations can be simplified to have representations which will carry only cosine term or only sine term. But we have discussed then, or we have extended the idea that suppose the function is defined in the interval 0 to infinity, then we have both the possibility of extending this function to make it as an even function, or we can extend it to make it as an odd function in the whole real axis. So, in either case the idea which is discussed here will be applicable, will be used, and we have a simplified formulation and the desired formulation. So, if we want to write this f x in terms of only the sine integral, we will extend it as an odd extension, and if we want to have the cosine integral, we will think as an even extension. So, for the Fourier cosine integral, the formula finally becomes a alpha cos alpha x, where a alpha can be computed with this rather simple integral. And for the, if you want to have Fourier sine integral representation, we can do with this help of this a alpha and this b alpha sine alpha, and the b alpha can be computed with this simple integral 2 over pi 0 to infinity, and we have f u sine alpha u du. So, that was that's all for this lecture, and I thank you for your attention.